Good afternoon, everyone. Good afternoon. Good afternoon. Thank you. So, after class today, I'll be sending out an email which will outline how we will take our exam. And if you look at the quiz results, which I have taken a look at, I read all your replies, of course, by the way. Okay. A majority of you wanted to opt for Plan 2, which is the online option, and having a 2-hour window to take the exam. I empathize with people who wanted Plan 1 but could not get it. We still live in a supposed democracy, so we will go with it. Okay, we will go with the majority opinion, all right? And I will send out a detailed email regarding how the exam will play out, how to access the exam, and then also the topics with regards to the exam, which include everything we cover until this week Friday, including what we cover on Friday. Okay, which is a continuation of Laplace transforms. So there will be one question on Laplace transforms for sure, the way we are going to solve it today and Wednesday and Friday. And there will be one question which combines rotational and translational systems. Okay, you will get a good fair crack at both the questions. It's an open book exam. I trust you all. I trust you all to follow the honor code. Okay, as much as you trust me, I trust you. So there is a symbiotic relationship here. Okay, so please uphold the integrity of an open educational system, please. Okay. All right, with that said, and watch out for my email. I plan to send it on the weekend, but typically, as you know, weekends, there are other things that take precedence. So I will be sending it out right after the lecture today. All right, thank you for your patience. We are looking at Laplace transforms to solve systems of ODEs, and that's my plan today. I'm going to take a very simple system, and then we're going to apply Laplace transform techniques. And along the way, we will come up with a way of generalizing this technique to other types of systems which could be more complicated. Right? So here is a simple example. I consider a spring mass damper system. Okay, very trivial system. This is M, K and C, stiffness of the spring. Damping constant, there is a force applied on the mass, let's say F of t. SCP calculations are not needed for this problem. The spring is not deflected at SCP. And this is a single degree of freedom system. We have discussed this multiple times. No need to harp on that fact. So I'm going to assume the degree of freedom to be x of t from SCP. All right, and then we're going to draw the free body diagram for a positive x of t. So when we are solving these problems, we assume a positive x of t, and we hereby get the equation of motion. Okay, so for x of t greater than 0, x dot obviously is going to be greater than 0 as well if you assume x of t to be positive. I have the spring in tension, and then I have the damping element in tension, and I have the mass drawn as follows. Okay, so there is the spring. Fs, Fs, Fd, Fd, this is also for positive, x dot of t, and we know this from what we've done in the past. Then you draw the free body diagram of the mass, the kinetic diagram, write the equation of motion. So mass F of t, equal and opposite forces where the mass is contacting these springs, so right there and there. Fs, Fd, right, and then I have the kinetic diagram, mx double double. And we sum forces in the free body diagram, equal to that in the kinetic diagram. Regular stuff, nothing earth-shattering going on here. choose a positive direction, end up with the equation of motion. Okay, I'm not going to write out everything. I'll write the final equation of motion. Okay, so final equation of motion is mx double dot cx dot kx is equal to f. Okay, no surprises so far. Then we look at the equation of motion. What's the order of this? This is a second order ordinary differential equation, right? So a second order ODE typically requires two initial conditions. Number of initial conditions is the same as the order of the ODE. Okay, so I need two initial conditions. I just want to write this down here. So number of initial conditions is equal to order of the ODE. If I have a single degree of freedom system of a second order, I need two initial conditions. If I have a springy pendulum, which is a 2 degree of freedom system in two-dimensional motion, I need 4 initial conditions, 2 for each coordinate. Okay? Alright, we will look at those problems as well in the future. So this is the equation of motion. In system dynamics, f of t is called the forcing function or the input function, as you know. So f of t is the forcing function. This is a function of time. This is an input to the system. And x of t is called the system response, right? Stuff that we've seen in the past. X of t is the output or system response. In system dynamics that we are going to study in this semester, f of t typically can be prescribed as a combination of the following general forcing terms or general time functions. Okay, so f of t can be given in terms of a step input, and it's sometimes called as a unit step input. We're going to discuss this today. Okay, so unit step. The symbol is u of t. This is what your textbook appropriates. Okay, so f of t will be prescribed as a unit step input. That's a symbol typically given for it, or sometimes as a ramp input. Typically r of t could be a sinusoidal or a harmonic input. This is sine AT, cosine AT, or combinations of sine AT and cosine AT. A sine AT plus B cosine AT. That's a harmonic input. Harmonic because everything is in nice back and forth motion. Okay, it's oscillating over time gently. And there is also this other function which is kind of weird, very different from the behavior of all of these, but actually derived from all of these. It's called the impulse function. Or in physics it's called the Dirac delta function, named after Paul Dirac, the famous physicist. Okay, we're going to spend some time thinking about how an impulse function looks like, and I'll tell you examples of where these could be used in real life. This is prescribed as delta of t, the Greek letter delta, little delta. Okay, so f of t could be a combination of all of these. F of t make sense to everybody? So typical systems, you will have combinations of these. What could be the example of a step input is, you have a vehicle that is approaching a pothole. The wheels suddenly sink in. Okay, or it's approaching a curb, the wheels suddenly sink in by a certain amount, and then the vehicle continues resuming its journey. That could be an example of a step input. Okay, and you'll see it looks like a step. An impulse input, you take a hammer, you impact the element, you impact the system. That's an example of an impulse input. On an impulse, you come and bang the hell out of it. But this is only lasting for a fraction of a second. Okay. Then you could have a ramp input, which is something that continuously escalates over time, like the difficulty of a course. Okay. And sinusoidal input, of course, you know how it works. Okay. Today I'm going to spend time on the unit step input. So the unit step input, or unit step function, is described in different ways in different textbooks, unfortunately. But we will stick to the definition that I feel your textbook, William Palm, has closest down to from an engineering perspective. It takes a value of 0 for time t less than 0, takes a value of 1 when time t greater than or equal to 0. And one can plot this as a function of time. I'm going to do it in the next slide, but before that, the unit step function is also called as a Heaviside function. It's another name for it, also called Heaviside function, named after Oliver Heaviside, once again a physicist from Britain, England. So typically the unit step looks like a step. Okay, so if I plot this, this is 0. This is the time axis. Okay, you can extend time onto the negative side. 1. U of t. Okay, this is the unit step function. It has a magnitude 1. It starts at time t is equal to 0. Even though this is a discontinuous curve, there is a discontinuity at t is equal to 0 because its value suddenly is different at the lower limit of 0. When you come to 0 minus, it has no value. When you come to 0 plus, it has a value. So what's its value at 0? That's the discontinuity. We are avoiding that deftly, sidestepping it, by defining the function to start from 0. Alright? So in doing so, we can prescribe a certain magnitude to the unit step, and that's what I'm going to do for our problem. So for our problem, let's give the following magnitudes or values for the parameters. So let f of t is equal to 2 times the unit step function, which means if the unit step function has a magnitude of 1, f of t has a magnitude 2, so many newtons. Okay, because we are looking at force. Then for some of the other parameters of our problem, let us say that the mass of the system is 1 kilogram. Just to give it some physical features, the damping constant is 3 Newton seconds per meter. Stiffness is 2 Newtons per meter. Okay, let's say these are the parameters that we have prescribed. And then we have some initial conditions as well. From now on, my shorthand notation for initial conditions is ICs. Okay, this is typically what you do in math as well. So x of 0, which is x naught, is equal to 1 meter. Okay, let's say somebody just gave this mass a shove of 1 meter at the beginning of time, and a velocity initially of 1 meters per second. So in any problem in system dynamics, certain things that will be given to you, the parameters of the system, the mass, spring constant, the damping constant. The input function f of t will typically be prescribed as a function of one of these foundational functions of time. The foundational functions of time being the unit step, or the ramp input, the direct delta, or the impulse function, harmonic inputs. Okay? And then initial conditions will be prescribed to you in the problem. Certain problems may have initial conditions, certain problems may not have initial conditions. And our aim is to obtain the system response, okay, for these parameters. So obtain x of t. And I want to quickly mention what is the Laplace transform of u of t. is integral 0 to infinity u of t, right? Because I'm now looking at everything starting from 0 all the way to infinity. What is the value of u of t? It is equal to 1. Okay, so this is just 1 times e to the power minus st dt, and so Laplace of u of t, if you do the math which we did 2 lectures ago, at the end of the lecture, this will end up being 1 by s. Okay. Another way of saying this is the inverse Laplace of this quantity is u of t, the inverse Laplace of 1 by s. I just want to write that as well here. The Laplace inverse of that quantity is u of t. So if I know the Laplace transform of a function of time, its inverse is nothing but putting it back into the time domain. Okay? Once again, I take the Laplace of a function of time, the result is in the Laplace domain. If I take the inverse Laplace of this person which is in the Laplace domain, I come back to the time domain, which is what I have shown here. Okay? So we switch between these two domains in system dynamics. We go from the time to the Laplace domain, and then eventually, after all the dirty work has been done, we switch back to the time domain, which is where I want my system response to be situated. All right? Okay. Before I solve the system, every system response can be broken up into 2 parts. Okay, so x of t can be broken up into x forced plus x free. X of t is the total system response that we seek in any problem. X forced is the response of the system to only the forcing function. Okay, sometimes I would like to distinguish between these two things. Okay, what is the response of the system to this particular force that is applied? Then I would also like to think, okay, what will happen if there was no force applied but only input conditions? That's x free, the response of the system to initial conditions. Okay, so this is the response to external force input. Force meaning it could be a force, it could be a torque, it could be a moment, it could be a couple, because torques and moments are also caused by forces. Yes, sir.
Is this the same as like particular and general solution?
Absolutely, 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 absolutely. Yeah. So you would call this as the particular solution, and you would call this as the general solution. Okay, but we are doing system dynamics. I refrain from using mathematical terms. This is the response to initial conditions. That's one type of system response broken up into these 2 parts, and we're going to do this for our problem. Okay. The other type, a little more insidious, is x of t is equal to x transient plus x steady state. SS is steady state. Okay, this is another way of taking a system response and breaking it up into these 2 pieces. Sometimes I would like to think, okay, I have a problem here. Okay, it's a problem of a motor responding to some kind of an input torque, a generator responding to an input torque. What are the terms of the solution that affect the long-term behavior of this motor? And what are the terms of the solution whose effect is only felt initially, but as time goes on, it just goes away? Okay, that's essentially what this breakdown here tells us. X transient refers to the portion of the solution that does not exist as time goes to infinity. So I'll write this down mathematically. So limit t tending to infinity, x of t transient is equal to 0. That is the definition of the transient part of the solution. These terms vanish as time goes away to infinity, as time goes on. And these terms here, the terms that do not vanish as t tends to infinity. So if I take the limit of these terms as t tends to infinity, I won't be getting anything useful. I would be getting a finite magnitude. All right? So in every problem that we're going to solve from now on, we will first start off with this particular template because we know that the problem has some initial conditions, the problem has some forcing response. We will solve the entire problem, do the Laplace transform, bring it up into an algebraic state of affairs, then take the inverse Laplace transform back into the time domain, and then we will eventually write the solution in this form as well. Where I am heading is this. Typically for stable systems, okay, I am interested only in this free part of the response, okay, and we're going to talk about this at the end of the class. So the free part of the response contributes to the transients. And in situations where there is no forcing function but only initial conditions for a problem, the entire free response is the same as the transient response. And if the transient response does not go away, then it is no longer a transient response, that's an unstable system. Okay, so we are now slowly getting to characterizing the stability of systems. But hang on to that. Okay, we are going to do this at the end of the problem. Okay. So back to our problem, we need to solve the following. So solve mx double dot, so m was equal to 1, so this is just x double dot, plus 3x dot, because c was equal to 3, and then k was equal to 2, plus 2x is equal to 2 times u of t, because the forcing function is twice a unit step input, okay? And the initial conditions that are given to me, x of 0 is 1, x dot of 0 is 1. So our aim is to obtain x of t and write it in all these forms. Okay, so obtain and we do this step by step. This is one problem today, and on Wednesday I'll take my time going over this. Then we will not be spending time solving stuff, we will be analyzing the solution. Okay? We will be using MATLAB. So, I take the Laplace transform on both sides. Two times u of t. In some other textbooks, u of t will be given with the suffix s, saying it's a unit step function of time. Okay, your textbook just uses u of t, so I'm going to stick with u of t. Take Laplace transform on both sides. This is Laplace transform of x double dot, 3 times Laplace of x dot, 2 times Laplace of x. Laplace of the step input with a magnitude of 2 is just 2 times Laplace of the unit step function, which is 2 times 1 by s, or 2 divided by s. Okay, so this is just 2 divided by s, Laplace of the unit step function was written there. Expand it out. Okay, use the definitions of Laplace of x double dot and x dot from the previous lectures. Recall, this is what we had obtained. So this is s square x of s, s times x of 0, x dot of 0, this was the Laplace transform of x double dot. Okay, then the Laplace transform of x dot, 3 times s x of s minus x of 0, 2 times x of s is equal to 2 by s. And please notice, this is just straight up math. Okay, the physics part stopped a long time ago. When we did the equations of motion, that's where you use the physics. Now it's a math part. All right? And then the last part is analyzing the solution, which is the engineering part. All right, I take the common terms, x of s, s square, 3s plus 2. Please watch this carefully. I take all the terms containing the initial conditions and bring them onto the other side, okay? While performing the substitution for the initial condition, this was equal to 1, this was equal to 1, this was equal to 1. If you do the math, this will end up being the following. So this is 2 by s plus s times x of 0 is 1, so that's just s. Then I have 3 times x of 0, which is 3 times 1 with a negative sign. I have a minus 1 with a negative sign, so that's 3 plus 1, 4. So that's s plus 4. Is everybody with me? This is just a simplification of everything else on that side. Okay, once again, the first s there, the extreme term on the right hand side, came from this guy here. S times x of 0, s times 1. Negative becomes a positive. Then I have minus x dot of 0, so that's minus 1, plus 3 times minus 1, so this is minus 1, and then minus 3, that's minus 4. Bring it onto the right hand side, that becomes a plus 4. So I have this s plus 4 term coming in here. And now, distribute the goodness on both these characters by bringing the term corresponding to the x of s. So this is s times s square, 3s plus 2, plus so this first term, and the reason why we're writing it this way is because this first term is containing contributions from the forcing function. This term is containing contributions from the initial conditions. So which means if I call this x of s as the Laplace of the total system response, then this term is x forced and this is x free, but in the Laplace domain. Okay, so I'm going to write this as x of s, this is the Laplace of the entire system response, the total system response. This is now x forced of s plus x free of s. Are there any questions so far? Bring it to this form, the rest of the stuff is fairly straightforward. Okay, now we just have to solve them. And that's my next step. start off by looking at x free. Okay, solve that, and then I get x forced. Yes, it's good.
So when you establish the forced and free for when you solve for x of s, right? Did you just set up the equation and then you could say when it's split in two, you can say the first one's forced, the second one's free, it doesn't really matter. You just define it as you please.
No. You see, the first one has a 2 by s term. Where is that coming from? That's coming from the forcing function.
Okay.
You see, and the second term has that s plus 4 combination because it's due to the initial conditions. Right. Okay. So this is not an arbitrary choice. This comes from the meaning of what the functions are. Okay. All right. I go to x free. Which is s square plus 3s plus 2. Now this s square plus 3s plus 2, it has a fundamental name. It's called the characteristic polynomial of the system. Okay. So this s square plus 3s plus 2 is the characteristic polynomial of the system. A second order system has a second order polynomial, a characteristic polynomial. Third order system, third order likewise. Okay. And what we typically would like to do before you start any solution procedure is to obtain the roots of the characteristic polynomial. And this is just a brief refresher. Roots of a quadratic. I have a quadratic as square bs plus c is equal to 0. I'm just writing it in the same form as what we have. The roots are s is equal to minus b plus or minus b square minus 4ac divided by 2a. This is a basic formula. I'm pretty sure all of you have seen this at some point in your life. If not, this is good. You can see it here. And so this is precisely what I'm going to do for our characteristic polynomial. I'm going to take this and obtain its roots. Okay, so the roots for our polynomial characteristic if I compare s square plus 3s plus 2 with a square plus bs plus c, a is equal to 1, b is 3, c is 2. Okay, so this is minus 3 plus or minus 3 square minus 4 times 2 times 1. This is the one and only time I'm going to do this. Okay. Obtain the roots. That's minus 2 and minus 1. If you do the solution, that's 9 minus 8. Square root of 8 is, square root of 1 is 1. And so I get real and distinct roots. Very important statement here. So s is minus 1, minus 2. These are real. They're real numbers, obviously, as you can see. And they are distinct. They're not the same. Okay, so they are real and why is this important to specify? Is because if my roots are not real and distinct, for example, if they are real and repeated, the solution procedure is different. If my roots are complex conjugates, which is what I'm going to do in the next class, my solution procedure is completely different. Okay? This is the simplest case. But we start with something simple and we build on it. So if this is the case, then I write my polynomial can be written as s plus 1 times s plus 2. Does this make sense to everybody? And so I'm going to go back to x free. Which was 2 by, s plus 4 by s square plus 3s plus 2. This is now going to be written as s plus 4 divided by this real distinct root combination. And I have a much longer explanation in my lecture notes that I'll be posting after class. But if you have real and distinct roots, you typically use the method of partial fraction decomposition. The partial fraction decomposition for real and distinct roots can be written as follows. This is only for real and distinct roots. It is some constant C1 by the first set of roots. So that's s plus 1. Then some other constant by s plus 2. Okay, so this is only for, this is the partial fraction for the real distinct case. This is not just for all cases. Okay, for a repeated case we are going to do that, and the complex conjugate cases we are going to do that. Okay. Okay, so we said about solving it.
Can you explain really quickly why one is forced and one is how do you know the difference?
I think we just went over it. Maybe I can explain it towards the end of lecture. Yeah. Okay. I think you were not around when I explained it. So. All right. So I take x free and then I move on to obtain the solutions. S plus 4 by all of that. Just rewriting it for my own convenience. This is C1 by S plus 1. C2 by S plus 2. Now here is what we do. This version, leave it as it is. Focus on these two. Once again, this is one time that I'm going to go through this slowly. Multiply both sides by the common denominator of s plus 1 times s plus 2. So here is what I get. This is equal to C1 by s plus 1. S plus 1, s plus 2. C2 by s plus 2. S plus 2. Quite laborious. I'll tell you a shortcut, but only after making you go through the pain. MATLAB can do this in maybe a millisecond. And we're going to go through that because we're going to solve more complex problems. But it is good to know these things. Okay, just because I can solve complex problems using finite element methods doesn't mean I should not know mechanics of materials. Okay, so this is also important, equally important. All right, so I cancel off that and that, that and that, that and that. So I have s plus 4 is equal to C1 times s plus 2. C2 times s plus 1. Many different ways to obtain the coefficients. That's what I'm aiming for, getting the coefficients. That's all I need. Okay. If I do this, if I substitute s is equal to minus 2, then I have minus 2 plus 4, minus 2 plus 2, minus 2 plus 1. Okay, I'm substituting the first case question.
You just pick minus 2 randomly?
Oh, randomly. Oh, no, minus 2 and minus 1 are the choices I'll be picking because they are the roots of the characteristic equation. Yeah, this is not a random choice. One second. These are not random choices. These are the roots of the characteristic equation. So I'm picking minus 1 and minus 2. I could have gone with minus 1 just to start off auspiciously, but this is good enough. So this is 2. That guy is 0, minus 2 plus 2. This is minus 2 plus 1 is minus 1, which means C2 is minus 2. Likewise, s is equal to minus 1 gives me the value of C1. Minus 1 plus 4 This is C1 times minus 1 plus 2, C2 times minus 1 plus 1, which is cancelled off. So 2 minus 1 is 1, so C1 ends up being 3. Okay. So I have the partial fraction decomposition, so I'm going to bring it out. So x free of s is now 3 by s plus 1 minus 2 by s plus 2. Okay? This is in the Laplace domain. To convert it from the Laplace domain to the time domain, I take the inverse Laplace transforms. So the inverse Laplace of x free of s is the inverse Laplace of 3 by s plus 1 inverse Laplace 2 by s plus 2. I would like you to recall the Laplace of e to the power minus at was 1 by s plus a. Which implies the inverse Laplace of 1 by s plus a is e to the power minus at. So we apply this to the x free. Inverse Laplace of x free of s becomes x free of t, because I'm now going to the time domain. Okay, so this tells me x free of t, that's the first term. The 3 is a constant. You can bring it out, so you can write this as 3 times 1 by s plus 1. The 2 is a constant. You can bring it out. So this is 2 times 1 by s plus 2, and obviously, as you can see from direct comparison, the Laplace inverse of 1 by s plus 1 is e to the power minus 1 times t. So this is 3 t to the power minus t minus 2 e to the power minus 2t. Simple, nifty, elegant. This can be done in 5 minutes on the back of an envelope. And this tells me a hell of a lot about a system. It tells me the system is stable. I'll tell you why in a minute. This is x free. X forced. I go back to x forced. Remember, I had erased it, but it was written as 2 by s times s square 3s plus 2. Look at this. I can write this as the following. S plus 0 is the same as s, so no harm done. S square plus 3s plus 2 is a characteristic polynomial which we had split into s plus 1 times s plus 2. So this is also equally valid. And I notice that all the roots in the denominator polynomial are real and distinct. So all of them real and distinct. And so if that is the case, then what I can say is I can use a similar partial fraction decomposition as the previous time. This is some C3 by S, C4 by S plus 1, C5 by S plus 2, where the C3, C4, C5 have nothing to do with C1 and C2. Therefore, a different part of the system response. Okay? Don't conflate the two. Does this make sense to everybody? I'm done with X free, the free response part of the system response. The forced part of the system response is still to be dealt with. This is the form we had. I wrote this as S plus 0. This was broken into characteristic roots, plus 1 and plus 2. S plus 1, S plus 2, real distinct case. That is the partial fraction decomposition. I'm not going to go over and find C1, C2, C3. It will be found in my notes. I'm going to write the values. It's the exact same procedure as what we used previously. So using the same procedure as before. We end up getting C3 is equal to 1. C4 is equal to minus 2. And C5 is equal to 1. And with your permission, I'm going to erase that panel there. I don't feel like moving the board up again. Is everybody good with this? And so I take the inverse Laplace of x first. Okay, so then I say, okay, inverse Laplace of x force, because I need everything in the time domain, because that's more visible to the human eye, right? Things move over time, oscillates over time, I can see them. Frequency domain, what's happening, I really have no idea. But we are going to do frequency response as well towards the end of the semester. So this is 1 by Laplace inverse of 1 by s, 2 times Laplace inverse of 1 by s plus 1, and then Laplace inverse of 1 by s plus 2. And same idea as before, inverse Laplace of the x forced is x forced in the time domain. So this gives me x forced in the time domain is Laplace inverse of 1 by s. Remember, the Laplace transform of the unit step response, recall, was 1 by s, so the inverse Laplace of 1 by s is u of t. Question?
Why is the inverse Laplace of like 1 over s plus 1 the only